Hi, I'm Yulun Liu from National Yangming Zhao Tong University. We present Boost MVS-NeRFs, boosting MVS-based NeRFs to generalizable view synthesis in large-scale scenes. This work is done by my students Zhihai Su, Zhiyao Hu, Shirui Cai, Jieying Li, Jingyang Lin, and me. Let's have a quick overview of generalizable NeRFs. In contrast to typical NeRF methods that requires time-consuming per-scene training, generalizable NeRFs take input views and directly render novel views in a feed-forward fashion without any training. This family of these methods, including MVS-NeRF, GeoNeRF, eNeRF, NuRay, and M4D, excels at synthesizing novel views without requiring time-consuming per-scene training. This generalization capability is achieved through a focus on pre-training, which allows these methods to produce high-quality renderings and impressive speeds at the same time. So compared to other per-scene trained NeRFs, they are pretty fast. However, while generalizable NeRFs offer impressive capabilities, they often suffer from limited viewport coverage and artifacts due to restricted input views. For example, the padding artifacts on the left in the case of MVS-NeRF and the artifacts in the red boxes of eNeRF. And even per-scene fine-tuning cannot resolve these issues. Our proposed method effectively addresses these issues. We integrate our approach with existing generalizable NeRF families, such as MVS-NeRF or eNeRF as shown here, which significantly reduce artifacts and expands viewport coverage in a feed-forward manner. And the scene can be further fine-tuned to boost quality. Notably, our method is train-free and universally compatible with previous methods. Furthermore, our end-to-end trainable framework supports fine-tuning to achieve even better rendering quality. We present a visual comparison between our method and previous approaches. The left side of the video shows eNeRF and the right side displays our method. eNeRF produces blurred rendering due to aforementioned limited viewport coverage problem, while ours are sharper and more realistic. This is also evident in the depth map comparison, while our method produces a more accurate reflection of the scene geometry. Let's first recap why existing MVS-based NeRFs suffer from limited viewport coverage problems. These methods render a novel view by first constructing a cost volume using several nearby input views. Then these methods sample rays and 3D points along the ray and query the density and color from MOPs to perform volume rendering and synthesize the output images. However, as you can see here, a single cost volume cannot achieve enough viewport coverage in the rendered image, resulting in padding artifacts highlighted here. Using another cost volume constructed by 3 different input views results in artifacts in different regions. Therefore, we propose combining multiple cost volumes during volume rendering to compensate for limited viewport coverage from each individual cost volume and improve the rendering quality. Cost volumes together strong. So the problem formulation becomes, how do we choose the best cost volume set from training views to maximize the viewport coverage? To solve the coverage problem, just naively combining arbitrary cost volumes might not be enough. We need to select the right set of cost volumes that actually make up the missing part. So we create the 3D visibility score and 2D visibility mask, which helps visualize the coverage and guide our strategic decisions. First, we sample points along the rays in the cost volumes. Then we project these points to determine if they fall within each viewport's coverages. The Boolean indicator of whether the points fall within the viewport coverage helps us calculate the 3D visibility scores. Finally, we can obtain the 2D visibility mask that represents the viewport coverage through volume rendering. Then we develop a greedy algorithm to select the support cost volume set and demonstrate how progressively combining multiple cost volumes improves the rendering quality. The main idea is to iteratively find the best mask that maximizes cumulative viewport coverage. In the initial state, we have several candidate cost volumes for selection. For each iteration, our greedy algorithm selects a cost volume that maximizes cumulative viewport coverage of the rendered view and progressively improves the rendering quality. In the first iteration, a single cost volume offers limited viewport coverage, resulting in padding artifacts shown in the orange bounding box with poor PSNR. In the second iteration, the selected cost volume compensates for the missing region of the first one and broadens the viewport coverage, thus alleviating the artifacts and improve the PSNR. And finally, as the number of selected cost volumes increases, the artifacts are eliminated. Here are more visual comparisons between eNeRF and our proposed method. To summarize, our Boost MVS-NeRFs enhance novel view synthesis quality of MVS-based NeRFs. It requires no training, adapts to any MVS-based NeRF in a feed-forward manner to enhance rendering, and supports end-to-end training for scene-specific fine-tuning. And that's it. Thanks for watching. Please check our project page and paper for more details and results.